For the last 6 years, I've been reading, reviewing, and responding to Christian apologetics books through my An Atheist Reads series. As I record this video, I'm a little more than halfway through what will be my final An Atheist Reads series, a response to Lee Strobel's The Case for a Creator. Thinly disguised as a work of objective investigative journalism, the book presents an argument for creationism, which was rebranded as intelligent design about 30 years ago following a U.S. Supreme Court decision that banned the teaching of creationism in public schools. In Chapter 7 of the book, Strobel interviews a creationist astronomer about the possibility that Earth is the only place where intelligent life exists. According to Strobel and his chosen expert, it's not only likely, but virtually certain that we are alone in the universe, that human beings are the only form of intelligent life anywhere, and that this is not a cosmic accident, but the work of an intelligent and supernatural creator. Earth being the only home for life in the universe is a desirable conclusion for creationists who are making not a scientific argument, but a religious one. The Bible teaches us that God created humanity and makes no mention of any other form of intelligent life, at least in the material universe. So, if science can prove that life is unique to planet Earth, it reinforces the truth of Holy Scripture. To creationists, anyway. But it's not only creationists who argue that life may not be as abundant throughout the cosmos as many of us think or hope. There are legitimate scientists who caution us not to get too excited about the prospect of discovering extraterrestrial life. And some of these scientists are advocates of what is known as the rare Earth hypothesis. The rare Earth hypothesis was introduced to the public in the year 2000 by the book Rare Earth: Why Complex Life is Uncommon in the Universe, co-authored by paleontologist Peter Ward and astronomer Donald Brownlee. In their book, Ward and Brownlee argue that the emergence of life on Earth was the result of a series of highly improbable circumstances. Circumstances so improbable, in fact, that we shouldn't expect to see them duplicated all that often throughout the universe. While cosmologists like Carl Sagan have popularized the notion that Earth is a typical planet orbiting a typical star, and we should therefore expect to find a universe teeming with life on many Earth-like planets circling many sun-like stars, Ward and Brownlee suggest that Earth may actually be quite atypical. They argue that we owe the existence of life on this planet to a long list of factors, not just the physical and chemical characteristics of Earth and the Sun, but also our location in the galaxy, the Milky Way being the right kind of galaxy, the arrangement of planets in our solar system, the stability of planetary orbits, the presence of a large natural satellite in a stable orbit around our planet, and the epoch during which we exist. To illustrate how rare planets supporting complex life forms might be, Ward and Brownlee devised the rare Earth equation. Similar to the Drake equation, the rare Earth equation produces an estimate of the number of Earth-like planets with complex life forms in the Milky Way galaxy. The rare Earth equation is written this way: n equals n asterisk times n sub e times f sub g times f sub p times f sub pm times f sub I times f sub c times f sub l times f sub m times f sub j times f sub me. N is the number of Earth-like planets with complex life in the Milky Way. N asterisk is the number of stars in the Milky Way. N sub e is the average number of planets in a star's habitable zone. F sub g is the fraction of stars in the galactic habitable zone. F sub p is the fraction of stars in the Milky Way with planets. F sub pm is the fraction of planets that are terrestrial rather than gaseous. F sub I is the fraction of planets where microbial life develops. F sub c is the fraction of planets where complex life evolves. F sub L is the fraction of a planet's total lifespan during which complex life is present. F sub m is the fraction of planets with a large moon. F sub j is the fraction of solar system with gas giant planets such as Jupiter. F sub me is the fraction of planets that have experienced a low number of mass extinction events. Like the Drake equation, the rare earth equation isn't intended to produce an actually accurate estimate of the number of Earth-like planets that support complex life forms. All of the variables in the equation require numbers that we can't really be all that sure of. Even the number of stars in the Milky Way galaxy is something that we can only make educated guesses at. Rather, the purpose of the equation is to summarize the main points of the hypothesis and to illustrate how improbable complex extraterrestrial life is if the hypothesis is correct. Ward and Brownlee propose estimates for some of the variables in their equation. However, they don't offer a value for n, the number of planets with complex life in our galaxy. But that hasn't stopped other people from plugging in their own values for these variables and solving the equation for themselves. And it's not going to stop me either. Estimates for the number of stars in the Milky Way range from 100 billion to as high as 700 billion. I have no idea, but Google says 250 billion, so let's go with that. The only planet that is indisputably within the habitable zone of our solar system is Earth, but it seems a little optimistic to say that 1 is the average number of planets in a star's habitable zone, so let's cut that in half and say 0.5. The concept of a galactic habitable zone is somewhat controversial, but Ward and Brownlee, who helped to develop the idea, estimate that only about 10% of stars are in the galactic habitable zone, so let's go with 0.1 for the value of F sub g. For the next variable, I found a Harvard study from a few years ago that used data gathered by NASA's Kepler spacecraft to estimate that 70% of stars in the Milky Way have planets of some kind. Just in case that's too optimistic, I'll cut it in half and go with 0.35. For the fraction of planets that are terrestrial rather than gaseous, I've seen estimates ranging from 10% to over 50%, so I'll split the difference there and go with a value of 0.25. Next is the fraction of habitable planets where microbial life develops. Ward and Brownlee believe this should be a pretty high percentage, perhaps even close to 100%. But I don't want to be too optimistic, so I'll go with a value of 0.75 for this one. Next is the fraction of planets where complex life evolves. Ward and Brownlee say this should be a pretty low number, so I'll go with 10%, 0.1. As far as the fraction of a planet's total lifespan during which complex life is present, let's use Earth as an example. Last year, fossils were discovered indicating that complex life existed as far back as 550 million years ago. Let's be a little optimistic and assume complex life will continue to exist for at least that long, for a total of 1.1 billion years. Let's also assume that the Earth's lifespan will be about as long as what we estimate the Sun's to be, 10 billion years. That means complex life will exist on Earth for 11% of its total lifespan, 0.11. The fraction of planets with large moons like ours is supposedly pretty small, so let's go with 0.1. Large Jovian planets could be fairly common if our discoveries of exoplanets can be trusted as representative, so let's say 0.5 for this one. And finally, Ward and Brownlee argue that Earth has gotten off lucky as far as mass extinction events, so let's guess that only 25% of planets have had sufficiently few mass extinction events. 0.25. When we plug these values into the rare earth equation and round the result off to the nearest whole number, we get 112,793. That's the number of planets we should expect to find supporting complex life in our galaxy, if the rare earth hypothesis is true, and if my values for the variables of the equation are accurate. I've seen other proposed solutions to the equation that yield values for n that are much bigger than the one I got. Values for n in the hundreds of millions, billions, tens of billions. I tried to be pessimistic in estimating the variables, and honestly, if you assume that the Milky Way has about 250 billion stars and that most of those stars have at least one planet, 112,000 planets supporting complex life is a relatively tiny number. If we assume only 100 billion stars in the Milky Way and keep all my other values the same, we still come up with a value for n of over 45,000. If we start with 100 billion stars and plug in values of 0.1 for every variable, we still wind up with n equals 10, which is really tiny, but is also larger than 1. It seems to me that if you want to use the rare Earth equation to argue that our planet is the only place in our galaxy that supports complex life, you have to be more pessimistic with at least a few of the variables than our present knowledge suggests we ought to be. And that brings me back to the beginning and creationism. The likes of Lee Strobel and those he interviews don't want to convince us that life is relatively rare. They want to convince us that it's foolish to believe life exists anywhere other than our own planet. But even if we assume the validity of the rare Earth hypothesis, and even if we solve the rare Earth equation using pessimistic estimates for its variables, we still can't escape the fact that while Earth may be one of the very few planets that supports complex life, it is almost certainly not the one and only. Co-creator of the rare Earth hypothesis, Peter Ward, agrees. In an interview with Nova published in 2011, Ward is asked if he thinks there is alien intelligence somewhere out there. He responds, "Yeah, I think there absolutely has to be. The numbers are just so great." Carl Sagan hit the nail on the head. Billions and billions, right? People made fun of him for that, but the reality is he was quite right. The numbers are so staggering. Billions and billions of galaxies with billions and billions of stars. Even if the existence of planets like Earth, planets where complex life is allowed to exist for long enough that intelligent life can evolve, is extremely improbable, there are so many planets orbiting so many stars in our galaxy and so many galaxies beyond our own that the existence of intelligent life somewhere else in the universe is extremely probable. Our nearest cosmic neighbors may live so far away that we never see them or even know they exist, but the odds favor their existence. Even if we do live on a rare and special planet rather than an average one, we are almost certainly not alone in the universe. That's bad news for anyone trying to peddle creationism, but it's good news as far as I'm concerned.